I would like to talk about our understanding of the superconductivity in semimetals that have almost dispersionless band in their band structure. The title of the talk and the talk itself will be different from what was proposed. However, I hope that you will enjoy as well. So this work was done together with my father. Here he's enjoying his yacht somewhere around Viborg and St. Petersburg district. So yeah, my name is Zyuzin. I'm from Aalto University, and my father is from UF Institute in St. Petersburg. Let me first introduce the materials that might have particles that behave almost dispersionless. You all know that the Dirac materials, the materials that have Dirac dispersion, so that electrons behave that is described by the Dirac Hamiltonian, they might have bound defects at the interfaces, at the boundaries, at vortices, whatever defects you may imagine in this material. And some of these bound states are dispersionless. And for example, this is one of the examples, the interface of graphite, that's with kernel stacking. And this surface state might have dispersionless nature. And some signatures of the superconductivity at the interfaces of graphite has been observed. Now, another example is very famous today is the twisted bilayer graphene, predicted a long time ago and observed recently. You all know that the Dirac dispersion of particles that live in graphene because it becomes flatter and flatter, and at certain twist angles of bilayer graphene, they become the Fermi losses become very low. Under certain theoretical conditions, it becomes perfectly dispersionless. And you know that the superconductivity has been observed in the twisted bilayer graphene at certain angles. And this is the review on this subject, on superconductivity. These figures are taken from there. Now, another class of materials that might have a flat band, actually they were predicted and observed recently. It's called so-called pseudospin 1 semimetals. Now, so I'm just showing you some representative example of these materials. This is the one that was predicted and observed. So in addition to the Dirac-like point at the center of the Williams zone, you might see almost dispersionless band that intersects the Dirac point. So this is the conduction band, this is the valence band, and here you have almost dispersionless band, which is dispersionless within some region, within some interval of momentum inverted and so on. Of course, you see that other bands can coexist with this flat band, and what is important for us is that we have almost dispersionless band, let me further call it flat band, together with some conduction bands. To us, it will not matter what kind of conduction band it is. All we need is that it is dispersive. All right. So what is our interest here? Our interest is to understand the superconductivity in such materials. And the physics behind that, we believe, quite straightforward. So we have, let's say, at least two contributions. For us, it will be enough right now. So we have a flat band contribution and dispersive band contribution. That's it. That's the simple model. Now, what means to have a flat band? It means that electrons that live at this band are strongly localized. Flat band means that the electrons are almost dispersionless. Now, the resulting Cooper pairs that might be formed out of these electrons are dispersionless as well. So it means that the resulting Cooper pairs cannot provide you the long-range coherence of the system. So it's not true superconductivity. Rather, we have preformed pairs that are very, very localized, right? Now, at lower temperatures, and due to other dispersive bands that allow you to have long-range coherence, we have eventually true superconductivity in the system. So that's the physics behind that. Now let's talk more about it. So we pick up the model of the pseudo-spin 1 semi-metal because it's just very simple. And we believe it might describe other situations as well. It's not important that we take the pseudo-spin 1 semi-metal model. Just to remind you once more, so you all know that there are direct materials like graphene, TIs, topological insulators, and so on, where there are band touching points in the brilliant zone where conduction and valence bands touch and behave almost linearly. The dispersion behaves almost linear. This is just a simple, very, very simple two-band model, right? Like in large metals, for example. Now, there are situations, for example, considered here, where this direct point is intersected by almost dispersionless flat band, as I showed you in the previous on the previous slide. Of course, it's not dispersionless completely, so there's a finite curvature. However, in this simple model, we take it to be dispersionless within some interval of momenta, and we say that the eigenvalue for it is just 0. And you see that there are two eigenvalues for the conduction and valence band. Now, the Hamiltonian describing these particles that live around this special point can be described by the simple Hamiltonian, right? So this is the Fermi velocity, momenta counted from this direct point, and this 3×3 matrix, right? So instead of usual Pauli matrices that describe the two-band model, here we have Gell-Mann matrices, right? Since we have 3 bands. That's the only difference compared to the, let's say, graphene. Now, what's the pairing model we will talk about? So we consider two values that have identical band touching points, identical that are described by identical Hamiltonians, and we consider even parity intervallic coupling. So we allow for the electrons to couple between the values. This is the chemical potential. And yeah, we have two contributions, right? We might have conduction electrons, we might have flat band particles. And we also consider the Cooper pair with total pseudo-spin 0. As you understand, we have 3 bands with pseudo-spin 1. So the resulting Cooper pairs might have spin 0, pseudo-spin 0, 1, 2. We pick up the simplest one, 0. Now, don't be afraid that we say that there's a coupling at the flat band, although the chemical potential is far away from it. This coupling will be allowed under certain conditions. When the coupling, when the interaction constant in the Cooper channel is larger than the critical, when some critical value. All right, so that is the pairing model. Very simple, right? 2 values, 3 bands. One is conduction, another one is flat. Now let's look into these two contributions. Here I wrote the green function for the conduction band electrons and for the flat band electrons. As you all know, this describes the amplitude probability for particles to travel from one point to another point at given frequency. So for the conduction electrons, we call it non-local, right? It is given by the usual form. It is proportional to the chemical potential, inversely proportional to the distance between the 2 points in real space. I recall that this is 3D. However, it's not important. And there's a usual exponent form, right? So this green function oscillates on the Fermi wavelength. Now the probability amplitude, or the green function, for electrons that live on the flat band is very different. It is proportional to the delta function in real space, which means that the particles, that the probability amplitude to travel between the 2 distant points is very suppressed. So the correlations are very local. Okay, so that's the main message here. So we have 2 contributions. They are drastically different. One is really local, and another one is non-local. Now, to look into the superconductivity in this model, we shall first consider the vortex part that describes the Cooper instability. And for that, we need to solve this equation, right? So this is determinant of this matrix equation, matrix expression, where lambda is the interaction constant in the Cooper channel, and P is just the usual vertex part in the Cooper channel. And it contains, well, just very simple, just you understand it immediately. So this is the green function for electron with momentum k, frequency omega, coupled together with electron with opposite momentum, opposite spin, opposite pseudo-spin frequency. What we need to do, we need to sum up overall, integrate overall momentum, sum up over the frequencies, and here's the temperature because we work in the Matsubara representation. Now, this vortex part, after some simplification, can be separated into two contributions. The first one is coming from the flatband contribution. Another one is coming from the non-local part, the dispersive band contribution. And you immediately see that the vortex part, which is described by the flatband contribution, does not provide you the long-range coupling between the particles. The resulting correlations are very local on the scale of a particle itself. However, the dispersive bands gives you long-range correlations between particles to form a Cooper pair, right? And you immediately understand that when you would insert the green function in momentum space for the flat band and for the conduction band, because of the dispersionless nature of the flat band, you will get a divergent integral, right, over momentum. By definition here in this model, we cut this divergent integral by the width of the flat band. And immediately we can introduce a parameter, a volume, which is inversely proportional to this integral, to the size of the flat band. Now, to proceed, let's first compare the vortex part contributions coming from the local part, flat band, and non-local part, dispersive band. This is it. Up to some coefficients, necessarily dimensionless parameters. You immediately understand that this logarithm is just the usual long-range DCS type of contribution. This is very familiar to you. And another one is just a constant when mu is larger than t, which comes from the flat band contribution. We will always consider when mu is larger than temperature. The chemical potential is larger than temperature. So what we have here is this ratio. And this means that, actually it means that the Fermi velocity, the Fermi wavelength Q divided by some volume, which is defined by the flat band. And when the Fermi wavelength is larger than the characteristic parameter that describes the flat band contribution, then the flat band wins. And we have a transition solely defined by the flat band contribution. All right. So here it is. And as you understand, the flat band cannot give you the long-range coupling between the particles to form up the Cooper pair. So resulting Cooper pairs are strongly localized. And the typical size of this Cooper pair is that volume Vg, which is defined by the size of the flat band. The wider the flat band, the smaller the grid, right? So we have a Cooper pair kind of sitting within a small volume. The order parameter on such a gray, on such a pair, is different from point to point. So as a result, the situation does not have long-range coherence. So it means that if you would look for the global superconducting properties, you won't see it. However, if you would measure something locally, then you would see some local gap over here. Just recall that in addition to these preformed pairs, we still have the contribution of the unpaired fermions that live in other bands. And now I will show that, later show that it is the presence of these unpaired fermions that will give you eventually the phase coherent state in the system. All right, now it's clear. So we have separation of scales. We have preformed pairs that are sitting locally. Of course, they move a little bit. We allow for this. However, this is not important. What is important here, there is no phase coherence, long-range phase coherence in the system because of the very local nature of the Cooper pairs. Now, let's look into this in more detail. So this is the Ginsburg-Landau functional written for the flat band contribution only. Here, the sum stands for the summation over all grains, or if you will, Cooper pairs. This is the typical logarithm of the hyperbolic cosine. It comes from the just the simple nature of the flat band contribution in the Ginsburg-Landau function. If you would vary it, then you will see that the gap or the local order parameter on a grain is proportional to the square root. Now you see that when lambda, the interaction constant in the Cooper channel, is larger than some critical value, then non-zero solution is possible. And this is the diagram when T normalized by the chemical potential versus interaction constant normalized by this critical value. And you see this green curve, which approaches on almost linear. This is the curve for the transition temperature for the delta. And you see that it approaches only almost linear dependence on the interaction constant at large parameters of the interaction constant, values of the interaction constant. And yeah, that is the story that about the flat band contribution to the superconductivity. Before people actually, the current status is that people believe that the situation here is just the superconductivity, that one can get the superconductivity solely on the flat band. However, we believe that the situation is a little bit different, and let me show why. So, in addition to the flat band, there are other bands, in our case, direct bands. However, it's not important. There might be other bands as well that provide you non-local contribution to the coupling between distant Cooper pairs. So you might think of a situation where you have very local preformed pairs with local deltas, like say like here grain 1, grain I, grain J, is separated by some distance Ri minus Rj. And you might think of this contribution as an Andreev coupling between the grains, right? Without this coupling, they don't kind of enjoy phase coherence. In the presence of this coupling, under certain conditions, the phase coherence might be standard, right? This contribution is proportional to, of course, the density of states at the direct band. So we, by definition, need to have finite density of states at the direct band to have this long-range coupling. Otherwise, it will not allow you to have long range. And it is kind of long range coupling. This is the 3D. This 3 comes from 3D dimensional. In 2D, it will be 2. Right, and these are just material dependent parameters. This is the density of states in the 3D case. All right. How do we actually take into account this contribution? Why? How do we find this transition to the true superconducting state? We adopt the mean field approach. You might think of a ferromagnet, right? A transition to the ferromagnet, where you have kind of a Heisenberg model, and the coupling to the nearest spins can be substituted with the mean field value. That's absolutely the same. We pick up some grain, let's call it delta naught, and the coupling to the rest of the grains through this Andreev coupling is substituted. The other of the parameters are substituted by their mean field value. So we're very close to the true superconducting phase transition. And this mean field order parameter can be found by calculating this ratio. where now the mean field Zyuzin functional is very simple, right? It consists of this local grain contribution and the coupling of this local grain to all other grains, which are substituted with the mean field solution. Here you can immediately recognize the typical BCS like Hamiltonian density of states, which is needed for the long-range coupling, right? So this is the phase diagram. So I just repeat this mean field equation here. So this is the kind of unusual self-consistent equation. You might not get used to it. However, it describes the mean field transition to the true superconducting state from the state with the preformed Cooper pairs. Now, when the interaction constant is much smaller than the critical value, recall that we don't have pairing on the flat band in this situation, right? So we are sitting here, so we're in the metallic situation. Then we get the usual, we reproduce the usual weak coupling BCS-like solution. That the transition temperature to the superconducting state is just has usual exponential dependence on the interaction constant and the density of states in this dispersive band, the zero band. Now, the presence of the flat band increases the density of states a little bit, and as a result, the critical temperature. So we're sitting somewhere here, right? However, when we overcome the critical constant value, so we might have the coupling with the flat band, the transition temperature to the superconducting state is different. It's not exponential anymore. And the vicinity of the critical value of the interaction constant is linear on the coupling constant, right? And it depends on the ratio of the size of the Cooper pair versus the Fermi wavelength of the conduction electrons. So the phase diagram, we believe that the phase diagram is different compared to what people believe to now. So we have a metallic phase at small interaction constant, right? Then when we increase the interaction constant, we can get into the preformed Cooper pair phase, where we have very local kind of disentangled Cooper pairs. And as we further increase the interaction constant, we can overcome the transition temperature to the true superconducting state. So we believe that this is the pseudo-gap state in this superconductor. So this is the result. These are results. So we proposed that the flat bands support Cooper pair preformation, and the presence of the dispersive bands can give rise to the true superconducting state at lower temperature. The main ingredient here is the separation of the two contributions. We have very local kind of a flat band that supports very local Cooper pair formation, and we have long-range coupling due to dispersive bands that give you the phase coherent state at low temperatures. And I think I'm done. Yeah, this paper was published recently in arXiv, so just have a look if you're interested. Thank you.
Vishwanath et al. And the various proposals, actually many of them, for superconductivity and the twisted by layers. So, I mean, is there some
explicit signature.
Yeah, exactly. The signature of your particular
scenario.
Yeah.
Right. The scenario is the presence of the pseudo-gap. So the preformed Cooper pair phase should be described by the pseudo-gap. So there's a kind of local versus non-local measurement difference. Frankly speaking, I don't know the proposals by Vishwanath and the authors. So what I just want to say is that actually we are working on the possible scenarios of this preformed Cooper pair formation in graphene right now. So I just don't want to talk much on that.
But maybe if I may add some comments, if you have some preformed Cooper pairs, you may you may find some signature in Josephson spectroscopy, maybe.
Yes. Here, no, not this way. Here, this way.
Yeah.
It's how about experiment? Yeah. So just a different slide on that. So there's a review by Benjamin Sassetta, Figerman, and Klapvik, quite a recent review on how to detect the pseudo gap or the preform QPPS. Here they review their work on the two-dimensional superconductors at the vicinity of the superconductor insulator phase transition. In particular, they were focusing on the indium oxides at the vicinity of MIT transition. Eventually, they just point on that how to observe the pseudo gap in these materials. That is, I think, might answer your question: what are the experimental signatures and how to distinguish between the two?
Okay. Do we have some more questions in Zoom or in the room, in the whole room? I don't know. Although I don't see any. If well, Ed, in case maybe, but I should discuss that. Well, you look only at the Cooper instability, but when we do a flat band, there are many other instabilities which are possible. I mean, if it will couple to phonons, you may have charge density wave and many other sorts of instabilities. Okay, which one will win? That's the number one question. And, can you say something about that?
Sure. So we will be always working at final chemical potential. So we would exclude the charge density wave here, or excitonic instabilities, I guess. Of course, if we would like tune the chemical potential closer to the charge neutrality, then of course other situations might overcome this pairing. And I also like to comment that we consider the simplest pseudo spin contribution. There are others in the multi-orbital, multi-band cases. What I want to say is that although situations might be different, there might be other instabilities in the system, but I would say that the scenario for the Cooper pair preformation is very general. So we have just two contributions. One is.
I do understand. No.
Yeah,
I understand.
that's it.
Maybe a second question, which is natural. So you have a criterion for this flat band to contribute, which is the Fermi wavelength to be larger than some inverse of volume.
Yes.
But for applying that to twisted bilayer graphene, for example, as to continue to know what will it be related to the Moiré length scale or not?
Well, I'm a bit confused to comment on that.
Because this Moiré length, that's what I'm afraid of, because this Moiré length is huge compared to the Fermi energy, and that may be, which would mean
Yeah, so I just don't want to comment on this too much. What I want to say is that, of course, there are kind of regions in this lattice which have this AA stacking and AB stacking, right? Well, the AA stackings, they have almost dispersionless nature of particles, right? Well, very flat. Now, the AB is kind of parabolic, right?
Yeah.
So that's it, I want to say.
Okay. I guess there is no other questions, and we need to move on. And I will have order, but I will ask you separately.
Yeah, thank you. Thank you, Pascal.
And okay, let's thank the speaker again.